Hi everyone. Today I'm going to talk about my project, Multi-Agent Reinforcement Learning in Indirect MFG Game. So first, some introduction. We will begin with thinking about a competitive multi-agent reinforcement learning, where each agent is acting selfish and they want to maximize their own benefit only. So this means everyone's competing with each other, and each agent and player's performance will depend on all other players. And there is a scalability issue, especially when the total number of agents is large. We can just think about the joint state and action space just expand exponentially as the number of agent increases. So therefore, we want to use the thing called mean field game to approximate the results of this competitive multi-agent reinforcement learning problem. It is a good approximation, especially when the agent population is large, and it can effectively reduce this problem into a single agent reinforcement learning problem. So here we need to talk about what a mean field is. So in the mean field, we will assume the population is infinite. And if we aggregate everyone, all my opponents, all other players' behavior, this will actually be the distribution of the state and action across the entire distribution. And then by assuming every player is homogeneous, is identical, interchangeable, we just consider a generic agent. Let's say that is me. I'm a representative agent. Then my own behavior deviation will not affect the overall distribution. So therefore, in the mean field game, it is just about having this representative agent to play against the mean field. So given the distribution and action and the states um, of the entire population, what will I do as a representative agent? Then my action actually represents everyone, so everyone will just follow my policy. So to begin with, we need to set up the problem. We have n agents, and we only consider discrete space. So h time t, that each agent will observe a state s sub I t. So that agent state at time t, and it will take an action according to its policy. So we just put everyone's states in a tuple, and we use st, this bold st, to denote this tuple, which is state vector. Then my reward is r of the bold s and my own action. And the transition kernel is my transition kernel, which is a function of the join actions and my own state at that time. So the agent problem is basically very standard. Start with S0, and we want to maximize the expected total discounted reward. Then let's say every agent is homogeneous. So the representative, the generic agent, will play against the mean field. Then we need to reset up this problem. So the tuple of state and action distribution is defined as the scripted L, which is the mu and V. This mu is the state, V is the action distribution. And my step reward right now is just myself, so I just get rid of the subscript I. Is a function of my state, my action, and also the mean field distribution at time t. And the transition kernel is defined in a similar way. My representative problem will just become, maximize my total discounted value, starting with state as 0, and just know the reward function right now has 3 parameters instead of only 2. This L is the extra one here. And my state transition follows my kernel, and my action follows my policy, which is I want to find out. Then what if this script L, this mean field, is not observable? Just think about in reality. It is very hard for everyone to know that while everyone else is like how many people is taking action 1 or how many people is taking action 2. Instead, we can only observe a signal, say lambda, which is a function of L. For example, the L is all players' market behavior. But in reality, how do we observe this market behavior? We cannot. We can only see a price, let's say lambda, which is actually a function of the mean field L. So the representative problem will be reformulated as follows. I just use a red circle to circle out to indicate that it was the mean field L, but we just replace L with something with a lambda. Then we propose this algorithm of indirect mean field game, which is very similar to the one I referred to. It's called Learning in Mean Field by Xin Guo and all her students. Um, so this algorithm will start with initial mean field L0, which is known to us but not known to the agent in this program. Then first we need to compute for each round. We need to compute the lambda k, the indirect signal, and then we just fix this lambda k and just feed it to the representative agent and let it perform the reinforcement learning to find the policy pi k. Then we just sample the action, sample the state, taking the action for all the agents in this game, and then with all this information, we can do an evolution of the mean field. So pictorially, it's works like this. So first this L, which is hidden to the agent but known to us, and we just get the associated signal lambda. We solve a reinforcement learning problem pi, and then we just sample the action and evolve the mean field to the next one. So one important thing is that if we run this game for k runs, we will be solving k reinforcement learning problems because each time we get a different a lambda, and with a different lambda, we will have a different strategy. If we use Q-learning, for example, and we run it for k runs, we will then start a brand new empty Q table each time the mean field changes. So let's say mean field changes for sure at every round. So in the beginning, we have L0, and associated with it is lambda 0, we get a pi 0. Then the mean field evolves. And then we solve L1, lambda 1 to get pi 1. And then it evolves again into L2 and lambda 2. We solve it for pi 2. And we just keep going on, going on. So each yellow box here, each brown box here represents a new reinforcement learning problem. So to analyze this algorithm, we first introduced that the thing called entropy regularization. We can just refer to the policy gradient lecture slides where we talked about that in class. Now, to simplify everything, we just consider a generic regularization function, let's say omega, which is a function of the action A. And if it is strongly convex, then the convergence can be possible for the algorithm I just presented. So we would just assume the strong convexity here. In fact, the one we talk about in class is strongly convex. Now we just replace the reward R by this regularizes reward by just adding that term or subtracting the function, a regularization function over there. So we would just replace all the R in our problem with R bar. Now we want to see after solving that many reinforcement learning problem, will the entire mean field game stabilize at an equilibrium point? So to define what the equilibrium is, we need to first define the operators. So for the mean field operator, defines as follows. First, we have the mean field, and in step one, we input that into this thing called optimality operator, and this operator will help us find the optimal policy pi. So here is basically just a reinforcement learning. You can view as Q-learning, PPO, natural policy gradient, whatever you want. But we just say, well, this operator will take the mean field and find the optimal policy associated with that mean field. Then, with the optimal policy and my current mean field, we just input them into this consistency operator. It will recompute the mean field, which functions as an evolution kernel. What does it mean? It means right now at time 1, my mean field looks like this, and my reinforcement learning is telling me to follow my policy pi. Then after I follow my policy pi, how can my current mean field at time 1 transition to at time 2? So this consistent operator is basically just about evolving the mean field. So at the equilibrium, we say mean field star and pi star, they form an equilibrium. Um, when I input Minfield star, the automatic operator gives me pi star. And at Minfield star, and I follow my policy pi star, the Minfield evolves back to the Minfield star. Then the thing is stabilized. The problem, the game is stabilized at this Minfield equilibrium. Therefore, if we look back to the previous slides, we just want to see after solving that many uh, reinforced learning problem, will in the end my L and lambda star at this pair, which is the mean field, and my policy from my reinforced learning will stabilize at equilibrium. All right. So to prove that this algorithm works, um, can the algorithm achieve the mean field equilibrium? We also need to make some assumptions. So first, we say under different indirect mean field signals, we solve different reinforcement learning problems. So we need to assume the reward function and the transition kernel are Lipschitz. So in addition that they are Lipschitz to the indirect mean field signal, they are also Lipschitz with respect to the states. The mean field update is Lipschitz with respect to the mean field L and the policy pi, which is the which is the consistency operator here. And also in the finally, we just say that the mean field signal is Lipschitz and single valued. This is the giving you the direct mean field, and the f function will compute the indirect signal, which is the price for us, right? Okay. So mathematically, the assumption looks like this. The Lipschitz reward is basically just R is less or equal to LR of lambda 1 minus lambda 2 of norm 1, and very basic here. And the transition kernel is also defined in a similar way. Then we can say the optimality operator, which is the one here, is Lipschitz. So that means my policies from different RL problems are Lipschitz with respect to the signals. The argmax of the Q-learning is Lipschitz with respect to the signal. So how do we prove that? The proof is very long. I think I wrote 3 to 4 pages just to prove that this is Lipschitz under these reward and transition kernel Lipschitz assumptions. It will use a combination of the Fenchel conjugate and dual norm, the strong convexity of the regularization term, and the boundness of the L1 term, L1 norm between the two distributions. So in the end, we will just arrive at this very simple conclusion that there exists this constant L1 that makes the optimality operator gamma 1 to be Lipschitz, which is my policy gamma 1. Then we need to assume the mean field update, the consistency operator is Lipschitz, and also my signal function is also Lipschitz. These three are usually given because they're not related to reinforcement learning. They're just I give the policy, I give the mean field, and they just behave, and it's all about the game simulator. And with that, with the theorem I just showed you and the assumptions here, we can actually use the Banach fixed point theorem to prove that the algorithm can achieve a unique mean field equilibrium whenever the L1, LF, L3 plus L2 is less than or equal to 1. So if we have this application that satisfies this condition, then and also satisfied all these assumptions, then we can say, well, the algorithm for that application problem, for that particular problem, can achieve a mean field equilibrium. So we just did an experiment using the power market. So we just assume like, we just say in this scenario, if every household has a battery, they can just sell the energy to the grid through the arbitraging. So we can just buy the electricity when it's cheap and charge into a battery, and when the electricity price is high, I sell the electricity in my battery back to the grid. And we just assume each household has this smart device to help them decide when to charge and discharge, which is when to buy and when to sell, using reinforcement learning. And since this is a power market, there are so many households. We can use the mean field game approach to approximate the solution. And the indirect signal here is the prices, which are the dual values from solving a linear programming. and it is proved to be Lipschitz um, with respect to the true mean field. And the network setup, we can just say 37 substations or buses on this network, and we have so many prosumers, consumers, just different type of customers uh, on this network, and they have some storage, and we also have all the generators. This is just for us to compute the electricity price. And in the end, we can see for the first 5 days, we just compare this to first with battery and the second without battery. So for the without battery group, they just don't do any reinforcement learning, and we can see the two curves are almost identical, and there's barely no learning. But in the last 5 days, we can see through the arbitrage, the smart decision with our mean field game algorithm. Um, the battery group, the learning group, actually successfully smooth out the price curve, make the price a lot less extreme. And what's more important is that for each day, we see here the pattern is very similar. That means the equilibrium is empirically achieved. All right, so this is my presentation. Thank you all for listening. If you have any questions, please just comment on the Brightspace or email me. Um, thank you very much.